according to the cloud. Let me get rid of this. So logic is an interesting topic because it's in many ways going to seem like we're just taking something that's fairly simple and making it more complicated than it needs to be. But in a lot of ways, that's kind of like what we do in math. It only just seems like that. The idea is to simplify things. It's to try to come up with general rules that apply in all circumstances, right? But it doesn't always seem like that's what the intent is. In a lot of cases, it seems like stuff like this is just designed to torture you, but it's not. Right? This is fundamental rules that really drive a lot of what happens in mathematics, specifically what we call discrete mathematics. Right? So when you start getting into things that computations involving probability and statistics, right? Not just your ordinary algebraic concepts, you find that this stuff finds its way in there more in a more prevalent fashion. Although it does work its way in substantially in an algebraic sense, but it's more fundamental when you get into the numerical stuff, so the discrete components or concepts. So statements, propositions, sentences that are true or false but not both. That's kind of an assumption that we have to make, that at least when we get into what we call propositional logic. And that's really where we kind of spend most of our time, because in mathematical sense, we don't really deal too much with the gray areas, like kind of true, sometimes true. It's usually true or false. Right. There are the rare circumstances where you have some sort of overlap, where something can be true under certain circumstances and false under other circumstances. But that's still propositional in the sense that depending on what those circumstances are, you would make a definitive statement of true or false. Right. We tend to stay away from the opinion-based stuff. Right. So the president is effective. True or false? I mean, aside from that just being a dangerous question in general, because depending on who the audience is, it could be, what do the kids call it? Triggering. The adults call it polarizing, but it's really just, it's opinion based. So that's why they do things like opinion polls, right? And data collection related to that, because it's not something that you can just pin down to true or false. And a lot of concepts in statistics, they try to determine truth value based off of something that could be considered opinion-based, based off of data collection. Right? That's not what we're going to do, because we're just trying to find the intersection between logic and geometry. So that's true or false. It's not like, is it a square? Well, in my opinion, no, that's not how it works. It's what are the circumstances surrounding a geometric figure being a square? Does it meet those requirements? Yes, then it's a square. No, then it's not a square. Does it meet some of them? Then it might be a square, right? But it might not be a square, right? But if we follow that path or the line of reasoning, a pathway, we can make a determination of whether the geometric figure is a square. There is a true or false at the end of each pathway. It's just a matter of going down that pathway. Right? In order to do that, we have to address certain logical connectives. We have the conjunction, disjunction, and the implication. Right? The conjunction and the disjunction are straightforward enough. The conjunction is very straightforward. The disjunction is, I'll call it straightforward with a twist, right? Which of course makes it not straightforward. Now, there's like one little component of it that makes it seem a little bit weird, but the very strange one is implication, so that requires a little bit more explanation. You can kind of tell based off of the length of the definitions which one is the most complicated one. But the conjunction is an and, right? Any and in a sentence is known as a conjunction. All right. We use a upside down V symbol, an almost capital A symbol, whatever you want to call it, kind of a triangle, but then the or symbol, the disjunction, is also kind of a triangle. But most people are comfortable just saying, oh, it's the one that looks like a V, right? But yeah, the conjunction is the and, right? And so only if both values of P and Q are true does the expression evaluate to be true, otherwise it's false, right? And so, I mean, there are examples that you can, you can just Google it, but I mean, this is a situation or circumstance or whatever the right word is, where you can just kind of think about it for a second and see that this sentence makes perfect sense. Only if, grammatically it might be a little iffy, but only if both values of P and Q are true does the expression evaluate to be true. Evaluate to be true. So if I give you an example, I'm saying I'm wearing a red shirt and blue shorts. I mean, I'm saying that I'm wearing both the red shirt and the blue shorts. So if I come walking in with the green shirt, then I'm lying, right? So AKA false. It's a false statement, and I'm just thinking about a situation where high school students, they're like, okay, everybody's gonna wear a red shirt today, right? And we're gonna dress up for Spirit Week or something like that. The red shirt and I guess blue shorts. I mean, I already used it. So red shirt and blue shorts. Right? Everybody's gonna do that. And then you come in, you're wearing your red shirt and blue shorts. So true for you. You're true. Right? Your friend comes in with red shirt and blue shorts. True for your friend. Another friend didn't get the memo. Red shirt and blue pants. Not shorts. So false. Didn't meet the criteria that was stated. Right. So, and actually, you can kind of even think about that as a kind of a triple conjunction, or triple component conjunction. It's really a double conjunction because there's two ands. Because if I say, well, actually, even four components. If I say you're wearing, I'll make a little note of it here. So, example, red shirt and I'll actually just write it out now. Blue shorts. I think my pen is dying. I charged it for a while today, though. I think it might be just skipping. All right, red shirt and blue shorts. All right, so if both of these conditions are not met, then the sentence is false. All right, so the elements that make up your conjunction need to be propositional in the sense that they have to have a truth value. There's no gray area. It's either true or false, right? There must be some way of evaluating, right? So, but what I was getting at here is that when I say that there's a red shirt and blue shorts, this could also be stated as, so AKA red and shirt and blue and shorts. All right, so where you're wearing a shirt that is red and blue shorts, so shorts that are also blue, right? The reason I'm mentioning this is because maybe the person that came into school got the memo. They knew they had to wear a shirt, shorts. One of them was red and the other was blue, but they didn't know that it had to be the red shirt and the blue shorts. Right. So it's a requirement that it needed to be red and a shirt at the same time, and also blue while also being a pair of shorts. Right. So kind of a tricky thing when you break it down to its most basic elements. a lot of the things that we talked about in everyday life, they can be really complicated when you really think about it. Right? So I am going to get in my car and drive to work. Right? So you think about all the things that have to go into that idea in order for it to be something that could actually happen. So I have to be a person, which I guess is easy enough, right? And I have to have a car. I have to then get in that car and then drive to work. So a lot of different base components that make the whole thing up. Now, when it comes to geometry, there's a lot of base components that make up situations too. But we'll get into that as we go forward, because when I don't want to lead off of that, because if I tell you that a square is a geometric figure that has 4 sides that are all of equal length and has 4 angles that are all of equal size, that's 5 components of an and state, right? So there's a lot going on there, and we'd have to make sure that every one of those things are true. And there are even other contributing factors to determine what makes something a square. So there's a lot, like I said, a lot going on. A disjunction denoted by the or symbol, right? The V, right? Or the upside down or the reflection of the and symbol, P or Q, right? P represents some statement, Q represents some other statement, right? As long as one of the values is true, the entire expression is true, right? So if I say that I'm wearing red shirt or blue shorts, then as long as I've satisfied one of those conditions, I'm telling the truth. The problem with a disjunction and the aspect of it that makes it confusing to people is that it makes it seem like a choice, right? So if I said I'm wearing a red shirt or blue shorts, and then I walk in wearing both a red shirt and blue shorts, and you'd be like, hey, you said you were going to wear a red shirt or blue shorts. You didn't say you were going to wear both. Well, the or the disjunction allows for the both to be a possible consequence. Right? So if I tell you, I mean, just thinking about it in a mathematical sense, if I tell you that, I'll just keep it simple, X is 2 or 3, right? I'm not telling you that it's a choice between 2 or 3. I'm saying if you selected 2 or 3, you're right. Right? Just think about it like a multiple choice question. Right? If you select choice A or C or D, you are wrong. Right? Any of those. Now, if you somehow selected all of them, you'd be really wrong. Which I suppose would be possible. I mean, it would be foolish, but it would be possible. But any of those would consist of the wrong answer. So that would allow the disjunction to encompass the entire set. All right. I'll get into more specific cases of this down the line, especially symbolic notation, because believe it or not, this is the kind of thing that actually gets easier when you get into the symbolic notation. When you start thinking about it contextually, it becomes a little bit more mind-bending. The implication, which is the mind-bendiest of them all, right? Denoted by the sideways arrow symbol. P sideways arrow Q is P implies Q, right? Or you could say if P then Q, right? Where P is the premise and Q is the conclusion. Sorry, right? So I don't think I wrote any of that there. So, oh, actually, I said if P then Q right there, so that's good. But P is also known as the premise. That's not a P. Kind of wrote it there. It's just sort of buried in my notation, my words. Q is the conclusion. All right. So I guess there's a little typo here. I forgot to write something there. There should be an A here. And so a few examples here. If my bread is green, then I will not eat it. I mean, I think that makes sense. If they like, I wouldn't want to eat green bread. So, I mean, it's an assumption that it's molded and past the expiration date. One usually coincides with the other, but you never know. Right. So the thing is, and I'll just read the blurb here. If the bread is not green, then it does not guarantee that I will not eat it. Right. So that's the thing. We know what will happen if the bread is green. We don't know what's going to happen under any other circumstance. Right. So that's where the implication gets tricky. Right. Because if you're given a premise and you satisfy that premise, then that's the obvious answer. So if I tell you that the bread is green, if the bread is green, then I will not eat it. Right? That's the promise I'm making. That's the conditional sentence. I mean, it's really the basis of contract language. Everything in a contract is conditional. Right? There are some statements, right, in a contract, like if you're contracted to work, like certain things like this is what your rate of pay will be. But there are other things that are conditional, like if you don't show up to work, you're fired. Right. But if I do show up to work, does that mean I won't get fired? No, if I show up to work, there are some things that I can do while at work that could get me fired. There are some things that I might not do at work, even though I'm there, like, work, that could also get me fired. Right? If I'm not living up to the conditions of the contract, then it's false. Right? But if I don't have any idea of what the circumstances would be if the premise is not met, then that's a different situation. Right? So, I have this whole blurb here about if you score a 90 or above in this class, then you'll get an A. Right? Seems reasonable. I mean, that's what the standard is. But what if I don't score 90 or above? What if I get an 88, but my teacher is really nice? I could still get an A. Right? So I didn't satisfy the premise, but the conclusion is still in play. It's still a possibility that I can get an A. Right? The only way that this becomes a violation is if you get 90 or above in the class and I don't give you an A. All right. So we think about false when it comes to, true versus false when it comes to an implication. The true is when the contract is satisfied. Right? False is when there's a violation in the contract. If there's ambiguity in the contract, then we still consider that a satisfaction. Right. So if I say, like, let's say, for example, I did not get, well, I'll just use the example that I gave before. I got an 85 in the class. So it's not true that I got a 90 or above in this class. But then my teacher was generous and gave me the A. All right. It's still a true sentence because my contract was fulfilled. Right? There's no violation in this contract. Right? That's what they call a loophole. Right? So I'll get to the symbolic notation in a second, but that's what really that boils down to. Right? So the biconditional, that's the weirdest one, because in terms of the way we would state it in a math class, like there's no legitimate expectation that anybody would use this verbiage in real life. But there are other ways of saying this in real life that get at the same idea, and that's when things get confusing. right? So the double arrow, right, double sideways arrow is read as if and only if. All right. So the phrase if and only if is abbreviated with IFF, so a second F on that. All right. So that's P implies Q and Q implies P, so both directions. I've never made a worksheet that I can't, or didn't make a typo on. This arrow should be the other way. All right. So I'm saying only when P is true, Q is true. All right. So the example, if and only if my alarm clock rings in the morning, then I will attend my morning class. And nobody speaks that way. All right. So, but it's kind of like if you, I don't know, emphasize certain parts of that expression, if and only if my alarm clock rings in the morning, then I will attend my morning class. Right? So that's kind of a little bit better way of kind of tying it together with the common vernacular. But it's more like the only way I'm going to class in the morning is if my alarm clock rings. I mean, the only way I can teach this class is if I can actually speak, for crying out loud. So, that's a more everyday way of explaining the same idea. It's still a biconditional, but there's really no indication of the word if in there, let alone if and only if. So making the connection between the everyday way of speaking and how we speak logically, and then therefore how we go about proving things geometrically, that could be kind of a bear, because what happens is, and this is why we're going over this, when I say prove that this geometric figure is a square, or explain why this geometric figure is a square, and students write it in their own way of kind of just speaking, oftentimes it's not logically sound. So the explanation is invalid, right? Because it doesn't follow the logic, right? And so if that happens, then, aside from it being wrong, like you will have not really gained anything from that discourse, right? So yeah, we want to make the connection between the formal logic and also the way everybody would normally say things, and really just kind of get at the idea of like what would be considered correct and what would be considered incorrect in the everyday way of saying things, not just the logic way of saying things, or the propositional logic way of saying things. So then you have that tilde symbol. That means not. That's probably the simplest part of this. All right, if you see a tilde, it means not, or it means the opposite. The opposite of whatever the statement is represented by the letter. All right, so if I say tilde P, I'm saying not P. If P is talking about, for example, I will wear a red shirt, then not P would represent I am not wearing a red shirt. Right? So that, like I said, that's the simplest thing. If you don't know the symbol, we don't know the symbolism, nothing is simple. But that's as far as things go, that's not bad. Right. So a little kind of a cheat sheet here. So A and B. I switched to A and B's for some reason. I have no idea why. A or B, if A then B, if A then B, or if B then A, not A. Now the triple equal sign, the triple horizontal line here, kind of like an equal sign but with an extra bar. We talked about congruence. That's the equal sign with a little tilde over the top, right? But that means something different. That's congruent. This is saying is equal by definition, right? Or by rule, right? So when we say by definition, we're saying by rule. There are certain things that we know to be true. These are just facts of nature, things that you learn the rule, and it's like, why is it true? because Pythagoras said so. That's why. And it's been proved over and over again. So for example, you might have seen a squared plus b squared is equal to c squared. But it's really a squared plus b squared is equal by definition to c squared. All right. It's cumbersome to write the triple equal. You know, you're doing it in an algebra class or computational skills class. If you had to write that triple equal sign every time, it'd be kind of a pain, right? But when you're given a rule and it's been proved, it's a theorem, and it's a triple equal sign technically. And this whole unit is, well, the whole part of the unit is about technicality, all right? This one is kind of strange. Little equal sign with a vertical little hatch there. B is true in every structure in which A is true. All right. So that's basically saying if A is true, then B is true. Assuming we use A as the premise. Right. So if we know that A is true, then as a consequence, we can prove B to be true. All right. But that, you know, we're a little bit away from that because that one's the mind bendiest of all of them, I think. And you'll notice that the symbol here, you know, this little inconsistency here, it's got an equal sign with a vertical, and then here it's just a single. The symbols mean the same thing, right? So,
Professor?
Yeah.
Sorry. Was that added? Because I can't find that on the sheet and I'm on page 2.
Oh. It was added at some point. I just don't remember when. Let me take a look.
The notation, my page 2 starts with the tables. It doesn't have the notation.
So, okay. So you don't have the notation at the top. All right. It might not have refreshed. Let me. Okay. So we're going to learn about truth tables. Now, truth tables are ways of proving sentences to be either valid, unsatisfiable, as in a contradiction, or satisfiable, which means depending on the circumstances, it could either be true or false. Right. So, yeah, it's an acquired taste. As you can see, it looks fairly complicated, but we can use it to determine the truth or under what circumstances certain arguments are valid. Right. And that's really what this comes down to, right? Determining the validity of certain arguments, right? So the first little table here, this is the conjunction P and Q. All right, now for the conjunction, this was stated on the previous page. So this is just going to be a fact at this point, right? So on the previous page, I was saying that the only way an and sentence can be true is if both parts are true, right? So this array of values here really just boils down to different possibilities if you have two sentences, right? So if I'm saying P represents the event or I guess I'll use event, that I'm wearing a red shirt, and Q is the event that I'm wearing blue shorts. It could be true that I'm wearing a red shirt and blue shorts. It could be true that I'm wearing a red shirt, but false that I'm wearing the blue shorts. It could be false that I'm wearing the red shirt, as in I'm wearing like some kind of green shirt or blue shirt or black shirt, whatever. But it could be true that I'm wearing the blue shorts, or maybe I'm neither wearing the red shirt nor the blue shorts. Right. So those are all the different ways that two statements in conjunction can have truth value. Right. They can either both be true, both be false, or some other mixture. Right. True, false, or false, true. Right. And the only way a conjunction sentence will ever be true is if both parts are true. Right. And so that goes back to what I was saying before. I know it's a lame example, but it's simple. I like going with the simple examples because the complicated ones are really, they start, driving a little insane. But if red shirt, blue shorts, right? If I say that I am wearing, like it's an in-person class and I'm going to show up on, next Wednesday, and I say, I'll be wearing a red shirt and I'll be wearing blue shorts. Mark my words. And I walk in and I'm wearing a black shirt, but I'm wearing blue shorts. It's still false. I said I was going to wear a red shirt and blue shorts. I didn't satisfy the claim that I made. Right? Now, if I say that I'm going to wear a red shirt or blue shorts, then the only way I'm lying to you is if I'm neither wearing a red shirt nor blue shorts, right? As long as I'm wearing at least one of those things, I'm telling the truth, right? If I happen to be wearing both the red shirt and the blue shorts, you're like, okay, that's overkill, but you didn't lie. I'm wearing a red shirt, but I decided to wear jeans. I'm still telling the truth. I'm not wearing the red shirt. I decided to wear a black sweater, but I'm wearing blue shorts for some reason. I'm not lying. I'm still telling the truth. Okay. So these become givens, right? So this is just the explanation for it, but it's not like you have to invent this every time. We'll actually use this information in order to evaluate more complicated situations. So the implication, that's the one where we're talking about a contract and whether I've upheld the contract, right? So implication, the if then, the blue shorts and red shirt here is a little trickier when it comes to an if then. If I'm wearing a red shirt, then I'm wearing blue shorts. It doesn't really sound like much of a contract. I like the if I go to work, then, or if I don't go to work, then I will get fired. Or if I get a 90 or above, then I will get an A. Those are more relatable. If I fill up my gas tank, or if I don't fill up my gas tank, my car will break down. Right. So any of those are kind of easier to sort of wrap your brain around. Right? Anything that is a condition that needs to be met, followed by the consequence for meeting or not meeting that condition. Right. So if I go with the grade one, if I get a 90 or above, then I get an A. Right. So I worked really hard. I got the 90. And then the teacher gave me an A. Contract upheld. All right. I worked really hard. I got a 99. Teacher did not give me an A for some reason. They hate me. The agreement was if I get a 90 or better, 90 or above, I will get an A. I did my part. I got the 90 or above, but you didn't give me the A. That means that you lied. The contract has been violated. Right? Now, the grayer area here, but it still makes sense when you think about it. If, again, the initial implication is if I get a 90 or above, I will get an A, then I will get an A. Right? So I get a 70, but the teacher gave me an A. All right? It's still true. It's still a true sentence. The contract has been upheld because I never said what would happen if you didn't get a 90 or above. I could still give you an A. I only said what would happen if you did get a 90 or above. All right. I said that I will give you an A if you got a 90 or above. You got a 90 or above. I didn't give you an A. That's a false. You didn't get a 90 or above, but I still gave you an A. I'm just a nice guy, but that has nothing to do with the contract. All right. So the contract hasn't been violated because it's not even in effect, because the premise hasn't been met. All right. And the same thing with false implies false. The contract is not violated because the premise hasn't been met, the contract isn't even in effect. All right. Now, the biconditional is basically P then Q followed by Q then P in conjunction. All right. So that it's a strange one, and it's actually pretty easy to prove. So let me see. Honestly, I don't even remember what I do half the time. Sometimes I surprise myself and I put things in notes and then forget. And then I reteach it anyways, like a side example. This one's kind of close, but it's not quite. All right, so I'll just do it off on the side. Let me just steal some room down here. Right, so P double-sided arrow Q is the same as P then Q and Q then P. All right. So what that means is if I can figure out what P then Q is, which we already know, and then what Q then P is, and then apply the conjunction rules to that, I can come up with the rules for biconditional. All right. So this will become the official first example of how to construct the truth table, or unofficial first example. So I'm going to make 2 columns, P and Q. All right. The breakdown again for 2 statements is that they can both be true. Maybe the first statement is true, but the second one is false. Maybe the first statement is false and the second one is true, or maybe they're both false. All right. So what we're going to do is separately, we're going to evaluate each of these pieces. First, I'm going to look at P then Q, which we already know because we just did it. That's true, false, true, true. All right, by rule. All right. Then I would need to evaluate Q then P. All right. Now Q then P is kind of a strange one because it's got the same elements as P then Q, just in the reverse order. So when we did P then Q, we looked from P. I'll use a green marker here. We looked at P going to Q. All right. So P was the premise, Q was the conclusion. So now we're doing it the other way around. Now I'm saying Q implies P, which means that the condition, the premise is Q, and the conclusion would be P. All right, so it's the exact reverse. There's no way this is going to be visible. That would have been nice. I was trying to color code it with the highlighter, but not really laying it out. Use this orange. There we go. All right. So I'm looking for true, then true. All right. Condition where the premise is upheld. All right. So that would be, again, I mean, it really doesn't matter what your perspective is. You can make up an example in either case, but really it's anytime you have a valid premise, but then you don't fulfill that with your conclusion, it's going to be false, right? When your premise is false, then the contract doesn't really apply. So it doesn't really matter what happens after that. The contract is technically upheld because there has been no violation, right? Because the terms of the contract have not been met. You're like, what do contracts have to do with geometry? You'd be surprised. We're getting there, right? So false implies true. So remember, we're reading this from right to left, Q to P. So backwards. False implies true is going to be true. True implies false is going to be false. False implies false is going to be true. All right. So a little hint. The only way an implication is false is if it's true then false. All right. So hint or shortcut, true then false is equal to false by definition. Otherwise, the result is true. Right? Every other combination of trues and falses will give you a true. The only one that gives you a false is true implies false. All right. So then what I would want to do here is take my P implies Q and put that in a conjunction with Q implies P. So I'm looking at these two columns that we just came up with, this one and this one, and I'm applying the AND rules to those. So the AND rule tells me that the only way you're looking at a true sentence is if both statements are true. Otherwise, it's false. Right? And the only instances where that happens would be the first and the last. Right? So the only time an AND statement is true is if both parts are true. So if it's false and true or true and false, the result is going to be false. Right? So what we have here is something that's partially true. So if we look at the definition, well, not really a definition, just the statements. If the last column is entirely true, we say that the argument is valid, meaning it's always valid. We call that a tautology. Tautology. If the last statement is entirely false, we call that unsatisfiable or a contradiction. That means that there's no circumstance in which that sentence will ever be true. Right? So it's always false. But then if it's a mix of true and false, we say that it's satisfiable, which means depending on the circumstances. And so you see each one of these is what we would call satisfiable. It just depends on the circumstances. All right. So the biconditional outcomes are TFFT, which we can now take as a rule, but it's satisfiable in the sense that it's not always true. It's only true if both parts are true or both parts are false. Didn't need to record that part of it. Determine whether the following sentence is valid, unsatisfiable, or satisfiable. So basically, all true, all false, or some true, some false. All right. So the first part is the conjunction. So that's our rule of and. That's all this stuff up here. Let me use a thicker highlight. All right. So it does get a little easier because if you're relying on the information that you already know, then it's kind of a copy paste job. So T, F, F, F. But you do want to consider why it's T, F, F, F. You don't want to just go through the motions there, but to some extent, you kind of have to, because otherwise, take you forever to do a problem. And if the whole purpose behind this is to actually aid in developing an argument, then stopping to consider why a conjunction sentence may be true versus false in order to evaluate a larger sentence, I mean, you get bogged down in that pretty easily, right? The disjunction, let me go back to yellow here. The disjunction is the second piece there. That's the or. So true, 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 false. And then the conditional, the implication. All right, so the implication, screen here. I'm highlighting it this way. That tells us that if the premise is true and the conclusion is false, then the sentence is false. So that's what I was saying down here. True then false is equal to false, otherwise it's true. So there is no instance in this setup here where the first part is true and the second part is false, if we're just looking at these two components. Okay. So that means it's true straight on down the line, which means that it's a valid argument. Right. Now, if I add a little context to this, now it's not going to be the most earth-shattering context. I'm just going back to the red shirt and blue shorts. If P represents I am wearing a red shirt and Q represents I am wearing blue shorts, then this would read as, if I am wearing a red shirt and blue shorts, then I am wearing a red shirt or blue shorts. So it's not the most intriguing argument ever, because if the first part is true, that means that you're wearing both a red shirt and blue shorts. So the second part then has to be true, because if you're wearing both a red shirt and blue shorts, then you're wearing at least a red shirt or blue shorts. Right? So kind of strange. Certain arguments seem like they're only designed to be part of a math worksheet, but we got to start somewhere, basically. Right? Now, number two, let P, Q, and R be the following statements. P is I have taken out the trash, Q is I have finished cleaning the dishes, and R is I've watched 5 hours of TV. Right? Now, you'll notice that there's a third column of truth values here. And that's because you can have many more, I mean, it's exponential. You could have many more possible scenarios involving true or false, depending on how many statements you have, right? Which is why things get more complicated when you get into the geometric applications of this. Because if you're talking about what makes something a square, I was talking about all those conditions before, there's a lot that can be true all the time. There's a lot that can be sometimes true. There's a lot that can be false, so there's a lot going on. All right. So this sentence that we're trying to evaluate, it says assume a child is good if blank holds true and bad otherwise. We would want to know under what circumstances, what conditions a child is good. So basically, any instance in which we get a true result here would be the case where the child is quote unquote good, right? But this would read as I have taken out, so I'm the child, I guess, in this situation. I have taken out the trash and I have either finished cleaning the dishes or I have not watched 5 hours of TV. Right? I mean, at first blush, it seems to make sense, right? Because if you think about like what would have to be in play in order for the child to be considered good, assuming that you value, like, I mean, as a parent, if part of the rules of, you know, the home front is, all right, your chores are to take out the trash and clean the dishes, and the reward is 5 hours of TV, although that seems like a lot, right? So maybe it's over the course of a week, even though that might seem like a little, you know, so maybe 3 hours, 2 hours of TV. So it just sounds like they're binge watching. It's probably not good. So what this is saying is I've taken out the trash. That definitely happened, perhaps. Let's assume it happened. Then the only thing that would be up in the air is whether the child finished cleaning the dishes, because the possibilities are the child is either going to clean the dishes or they're not watching 5 hours of TV. Right? Now, there is a flaw in an argument here, or in this argument, that any child would latch right onto if it's specifically stated that you're going to watch 5 hours of TV. Well, the kid would say, well, I didn't take out the trash, I didn't clean the dishes, so I won't watch 5 hours of TV. I'll just watch 4. I'll watch 4 hours and 59 minutes. Or they really want to be slick about it, I'll watch 7 hours of TV. Because if the statement is true or false, watching 5 hours of TV, no, did you take out the trash? Did you wash the dishes? No. Did you watch 5 hours of TV? Because I swear, if you watch 5 hours of TV, you're in so much trouble. I did not watch 5 hours of TV, I swear. I watched 4 hours and a half. And so these are things that come into play. You know, that's the logic of it. And I think sometimes children intuitively understand logic better than we do. So all the different possibilities for these statements. Now, each one of them in and of themselves could be true or false, but together, you could be looking at all of them being true, all of them being false, and every other possible combination. Maybe 2 of them are true and 1 of them's false, 2 of them are false, 1 of them's true. You know, so we got to account for every possibility here. All right. So Q or not R. All right. So we have Q or R here. All right. So I need a not R. So what I tend to do here is just kind of tuck it right in there. All right. So I'll make a skinny little column here, you know, adjacent to the Q. And I'll call that not R. Some people could do this in their head, but you know, even if I were comfortable doing that right now, I wouldn't do it. This is the first time we're learning about logic, so I wouldn't do that. So not R is going to be the opposite of whatever R is. All right. So if R is true, then not R will be false. Let me make this red actually. Oh, dang it. So false, 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 true, 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 true. Because I'm just looking at these items here. Not R is just the opposite of those things. All right. So when I'm looking for Q or not R, I'm comparing, I forgot what color I used, yellow. These two columns. And the only way an or sentence is false is if both parts are false. All right. So going down the line, I have true. This one would be false. True. This one would be false. True, 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 true. Again, only if both parts are false will the whole sentence be false. All right. So then I'm looking for the conjunction between the P and what we just came up with, the Q or not R. Conjunction would only be true if both parts are true. Right? So that's true, false, 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 true, true, false, false. Right, so I just took these two columns and applied the conjunction to it, right? Or the conjunction rule is what I should say. So there are multiple instances in which the child can be considered a good child, right? But that would be, I mean, it's limited to just those few situations, right? So you'd have this case here, this case here, and this case here. So it is satisfiable. It's not a valid argument because it's not always true. It's not unsatisfiable because it's not always false. It's satisfiable. It depends on the circumstances. All right. So again, our whole sentence originally here was P and Q or not R. So if P, Q, and R are all true, we would have satisfied the conditions of the argument. All right. So if I take a peek here, so the child took out the trash. Right? It was true that they took out the trash. It was true that they finished cleaning the dishes, and it was true that they watched 5 hours of TV. All right. So if you read that in the sentence, it's saying, I have taken out the trash and I have finished cleaning the dishes, or I have not watched 5 hours of TV, just plugging it right in as you see it. All right. So as long as each original sentence statement was true, that would be a valid sentence. All right. So we would call the child good under those circumstances. Another one would be true, true, false. All right. So the child took out the trash. They finished cleaning the dishes. They did not watch 5 hours of TV. Right? I mean, based off of that sentence, it's possible, right? Because it was an or. You know, they did what they needed to do, but nobody's going to force them to watch 5 hours of TV. Maybe they just decided not to. It seems to make sense. And in fact, that might make the child, the parent, consider the child to be really, really good, right? And then we have true, false, false. And that would be the instance where the child took out the trash, didn't finish cleaning the dishes, so therefore, you know, not able to watch 5 hours of TV. So in the first two instances, the child was considered good because they did everything they were supposed to do, and they received a reward, right? Or they chose not to receive the reward. But in the last one, didn't do everything they were supposed to do, but then didn't watch the 5 hours of TV. So they didn't go looking for something they weren't entitled to. Right? So in those circumstances, the child would be considered good also. It's like they took their medicine. They knew that they weren't allowed to watch TV. So because they didn't finish what they needed to finish. So that was it. And it may not even be a punishment, it may be a time factor. Maybe there just isn't 5 hours available to watch TV because the individual took too long to complete the dishes. So, there's a lot of different reasons why that might be the case, but it's really beyond the justification because it's not an opinion. It's what are the circumstances that would make the sentence true. All right. So the next one, same idea. I mean, even you could even look at it with the same context, the P, Q, and R. So we have P and not Q, right? Again, I would make another column for not Q. Some people like to adjust the Q column, just kind of negate it and just overwrite what's there. That's fine too. But what I would be looking for here is to first address the P and not Q. Now, the way this sentence would read would be, if I have taken out the trash and I have not finished cleaning the dishes, then I have watched, or I will watch, depending on tense, 5 hours of TV. Right? Seems kind of like an iffy situation, but it's just another argument to consider. Right? So, in order to meet the premise, you have to take out the trash and not clean the dishes. Right? It doesn't necessarily mean that the child is skirting their responsibilities. It could be the case that maybe one of the siblings is responsible for the dishes. So I have taken out the trash and I am not going to clean the dishes because it's Samantha's turn to clean the dishes. It doesn't matter what the reason is behind it. This is just the argument. So this is just basically saying, as long as I uphold my responsibilities, then I can watch my 5 hours of TV. Although I still think that's a little insane. So not Q, just like I did before, I'm going to make another column here. I'm going to call it not Q. And then we're going to evaluate, keep forgetting what color I used. Green is implication. So I'm going to take this column, and then whatever we come up with for this column, and that's going to give us this column. So the not Q column is just the opposite of everything I have in Q. So I'm looking for the conjunction between the two columns that I have highlighted in green. Although this one's kind of a little, I'll just do it again. All right, so conjunctions are only true if both parts are true. All right, so both parts are not true here. Both parts are true here. It is not the case that both parts are true here. It is not the case that both parts are true here. Same here. Both parts are true here. It is not the case that both parts are true here. It is not the case that both parts are true. All right. It's kind of weird because I was saying, and initially I was saying both parts are not true. But what I was trying to say is it is not the case that both parts are true. Those mean two different things. If I say both parts are not true, I'm implying that both parts are false. Whereas if I say it is not the case that both parts are true, I'm allowing for any other circumstance except for true and true. Right? It's very subtle shift in the way of speaking that allows for more logical precision, which is why in math textbooks and stuff like that, it's so weirdly worded. That's just the nature of it. Right? So P and Q implies R would be my next column. I got my color scheme. These are all supposed to be blue. I mean, it's not really the end of the world, but I'm trying to be somewhat consistent here. So I'm now looking at the P and Q implies R. So here's my R. Here's my P implies Q. I'm sorry, P implies Q. P and not Q implies R. All right. So it's the direction going from this conjunction P and not Q implies R. So the arrow is going this way. Right. And so with an implication conditional sentence, the only instance in which the sentence is false is if true implies false. Right? True is the premise, false is the conclusion. That only happens here. Everything else is true. All right, so this is another satisfiable situation. It was almost completely valid. It was almost a completely valid argument, but there was one loophole in there. And that one instance where it wouldn't necessarily be true. Right. And so that would be the case. Just going back to P, Q, and R. That's just an ordinary arrow, old school arrow. P is equal to T, as in true. Q is equal to false. F is in false. R is equal to F is in false. Right. That's just one single solitary circumstance. All right. So what that's saying is, just going back to what the statements we're talking about, taking out the trash, true. Didn't clean the dishes, didn't watch 5 hours of TV. Right? And it's the only instance in which it would be a false sentence. Right? So then we get into logically equivalent statements, which is where things start getting a little bit easier. Right? Although the truth tables, they're always involved. There's a lot of ingredients that go into them. But when it comes to reasoning, once you start understanding what the different relationships are, it goes a lot quicker. Right? So logically equivalent statements are statements that always have the same values, right? Not necessarily that they're always true. It's just that they have the same values as one another, right? So an example of which is, they call it a contrapositive, but if I take the premise, and I get to it down here, in this area here, but a contrapositive is where you switch the premise and the conclusion, but negate them both also. So an example of logically equivalent sentences, and I think it would make sense. So quick example, if I study, I'll just use what I have here, I will pass. Give myself a little bit more room. All right, and this will have the same truth value as if I do not pass, I did not study. Ah, come on. There we go. All right, so these two things mean the same thing. If I study, I will pass. If I don't study, I'm sorry, if I did not pass, I did not study. I do not pass, I did not study. Tenses are always a little trickier, but no, I mean, I think most people would agree at first glance that that seems to make sense. They seem to mean the same thing, right? What happens if you study? Under most certain, like assuming everything goes to plan, if you study, you're going to pass. Right? It doesn't always play out that way, but let's just assume that it does. All right. So then you would think that if I didn't pass, so assuming that that sentence is true, then if I didn't pass, then the natural conclusion would be that I didn't study. All right. So that's the bargain. So the thing is, the premise and conclusion is based off perspective. So from a teacher perspective, I look at it like, and most teachers do too, but like it's not always true. It's just the initial response. Like if a student failed a test, it's like, what happened? You didn't study? So that's if you did not pass, it's because you didn't study, right? And most people think, if I study, I will pass, right? That's a logical way of thinking about it, but it doesn't account for the eventuality or the premise of what will happen if you don't study. Right? It doesn't mean if you don't study that you're going to fail, because we've all been in situations where you didn't study for a test and somehow you passed it. Like, I don't even know how I did that. And then there have been plenty of other situations where you didn't study and you failed, or you studied really hard and you still failed. So every possible outcome is on the table. Right? But if the original premise doesn't address the point of concern, then there's no way you could say that the contract has been violated. So if I tell you, if you study, you will pass, and then somebody comes walking in having not studied at all, and then passes the test and said, "You see, you lied. You were so full of it. I didn't need to study at all." I said, "I didn't say what would happen if you didn't study. I only said what would happen if you did study." All right. So now, if you did study and yet you failed, it's a different story. Right? Then it's a breach of contract. All right. So we have another way of determining logical equivalence, and that would be using a truth table. Right. So aside from just kind of playing it out in your mind and reasoning it and seeing if it makes sense, which is always a dangerous proposition, you can create a truth table. All right. Now, I'm looking at P implies Q versus not P or Q. All right. So P implies Q. If I study, then I'll pass the test. Assuming P is I study and Q is I'll pass the test. P implies Q is if I study, then I'll pass the test. Not P or Q is I don't study or I'll pass the test. Right. Now that one seems kind of weird. I mean, I don't know if too many people would say that. So you're reviewing for a test. You're in a class. You decide you're not going to do anything. I'm not going to study. You could say, but I'll pass the test. And I'll pass the test. That seems to make sense. I'm not going to study, and you know what? And I'm going to pass the test. Okay? That seems to be the way somebody would speak. I don't study or I'll pass the test. It just seems kind of weird. So Now, now throw the word either in there, it kind of cleans it up a little bit. Either I don't study or I'll pass the test. Okay, a little bit better. Now, if I tell you that a disjunction is commutative in that you can swap the first part with the second part, doesn't matter what order you put them in, it's still equivalent. Either I'll pass the test or I didn't study. Now it makes sense. And just slight phrasing change, tense change, it goes a long way. And now it comes to creating the truth table. We do that for the purpose of really not like locking it down and making sure that what we have here makes sense. Okay? So true. So my p-value, it could be true that I studied, it could be true that I passed the test. It could be true that I studied, but false that I passed the test. It could be false that I studied, but true that I passed the test. Or maybe I didn't do it. Okay, I'm just a big old slacker. I didn't study and I didn't pass the test. So actually, honestly, to be fair, this one is probably the slacker. This is kind of expected. You know, if you don't study, why would you expect to pass? Right? Now, there's certain things that maybe you don't need to study. And in certain courses, studying is defined differently. Like in math, studying is like just doing more practice problems. Whereas in biology, studying is like memorizing the definition of mitochondria and stuff like that, which I only know because my son was taking a test the other day. The powerhouse of the cell, right? I don't know what that means, but it's the buzz phrase. But yeah, anyway. Nucleus and what's the other one? Golgi apparatus. Never heard that one before. Golgi? I don't know. But yeah, yes, I'm learning a little biology as I go. It's crazy. Not enough to take a class or pass a class. That was, you know, like when people say math is my weak subject, I say things like biology is my weakness. History, basically any subject area that required any sort of memorization whatsoever. I'm just not interested. So here I am talking about studying and passing tests. You know, of course, hypocrisy. My name is. So anyway, what we're gonna do is, oh yeah, no problem, yeah. So first we're gonna look at that not P. It's like, where does not P come from? Well, we have two things that we need to evaluate. We have to evaluate the conditional, and we have to evaluate the disjunction, right? But part of that disjunction is a not P. So sometimes it helps to just kind of itemize it and make a fresh new column for each little element, right? So not P would be the opposite of P, right? So yeah, I think no, yeah. I mean, it's so weird that I care about the highlight colors. I don't know why, but I do. I don't know why. But the
highlight colors are definitely helping keeping everything.
Oh, they are? Okay, so it's not weird at all. It's very well planned out on my part. I appreciate that. So the disjunction is the case where if both parts are false, then the whole thing is false. Otherwise, it's true. So when I look for not P, I'm taking every element of P and negating it. So the opposite truth value. But then I'm taking the not P and comparing it, use the word compare loosely, with Q using the disjunction process. Right? So not P or Q. Now I have a column with not P and a column with Q, right? Because disjunctions are commutative, right? And again, that's it's a fairly common math term. It doesn't mean you think about it all the time. Commutative means that it's the same in both directions. I always think about it like commuting to work. So I go there, I come back. Right? Same path there, same path back. Not always true. Sometimes, like especially if you've ever driven on the Merritt Parkway, you know that sometimes you want to go one way on the Merritt and the other way back roads because of the traffic. But assuming that it's the same path in both directions, the example of commutative, as in commutative property and commute to work, would make sense, right? But for addition, you could add two numbers in either order. 2 plus 3 is the same as 3 plus 2. Same thing with multiplication. Same thing with ands and ors, conjunctions and disjunctions, right? So I can read this just as it is and still get the same truth value that I would if I swap the two columns, right? But either way, I'm getting true, false, true, true. But again, the only way a disjunction is false is if both parts are false. All right. Now, if I study, then I pass the test, or I'll pass the test, P then Q, that goes back to the original set of values, truth values. Okay, and we follow the rules for a conditional. Rules of a conditional say, if the premise is true and the conclusion is false, then the whole thing's false. Right? That's the breach of contract that I was talking about. Otherwise, it's true. So true, false, true, true. Right? So what we have here between these two columns is logical equivalence. Heck of a box. Logical equivalence. All right. And that's because we have two different expressions, two different sentences that give the same array of truth values in the same order. So if I study, then I'll pass the test, it means the exact same thing as I don't study or I'll pass the test, which is weird because it's like one of them sounds like something that you would say in everyday life and the other does not. But the rephrase on that second sentence there, I'll pass the test or I didn't study, like I said, just playing around with the ordering, playing around with the tense goes a long way. All right. Now, I don't even know why I have this last column there, except to show that it's a tautology. I mean, or a valid sentence. So the P implies Q, then not Q or I'm sorry, not P or Q would be true right on down the line because you're evaluating the truth value of these two items here. And no matter which direction you go, it's never going to give you a false outcome. Right. So this is valid, but it doesn't really add anything to the conversation. So I kind of regret putting it there. Just because, I mean, if I were to read this, it's the most convoluted thing. Maybe that's the thing. You're going to be a contract lawyer, not like the kind who works on contracts or gets paid as part of a contract, but like you actually evaluate contracts to see if they're logically sound. You may like sentences like this, but this is a weird one. It would read, if, so it's a double if situation. If I study, then I'll pass the test. Then I don't study or I'll pass the test. And so there really isn't any true value in this last one. It would actually make more sense as a biconditional, because that's when you really get into logical equivalence. But I'm happy with this because that gets the point across better than anything else. Okay. So the next example, let F represent I eat the right foods. Let S represent I get sick. So you have a couple of sentences, and what we're going to do is express them in symbolic form, then determine if the two compound sentences are logically equivalent, right? So if I eat the right foods, so that's F, then I don't get sick. Well, S is I get sick, so I want the opposite of that. I don't get sick, or I don't eat the right foods. So there's two ways to handle this. One would be to make a brand new truth table, but we got to start thinking, all right, we have to be learning something from these truth tables, like some facts, some rules. You know, if I tell you to solve the equation x plus 2 equals 3, you know, I'm going with a very simplistic example for a reason, but if I tell you to solve x plus 2 equals 3, and you go through the process of solving it, and you get x equals 1. And so you did that as part of a review or maybe a homework assignment. And then that question comes up on a test, and let's say it's a multiple choice question. Hopefully, I mean, the thought is that you remember the answer and that you would just go right to the answer. Like, oh, the last time I did this, it was 1, so it's going to be 1 again. A better example is products and square roots and things like that. You know, like you go through the process of memorizing multiplication tables, but when you think about like how you first learned to multiply, I mean, everybody kind of, I don't want to say everybody learned it a different way, but different age groups learned it a different way. The most current way is by like number bonds and stuff like that, which is too much to explain in this moment, but not, I don't know too many people who want to hear it anyway, at least not right now. But when you think of something like 5 times 6, you know, you might think of it as 5 6 times. Right? So when I'm explaining the concept of multiplication to a young person, I say, what's 5 times 6? They say, I have no idea. And then I say, what's 5 6 times? And a couple of minutes later, maybe that's an exaggeration, a couple of seconds later, they come back with 30. Because they're like 5 6 times. What could he mean by that? 5, another 5, another 5, another 5, another 5. How many 5s do I have so far? I'm up to 25, one more 5. I'm up to 30. Oh, 30. Is that what you mean? Yeah, that's what I mean. All right. So the next time you see 5 times 6, you're not going to do that again. You just know it. You know, it's a fact now. That's why they're multiplication facts, right? You use those basic facts to help you evaluate more complicated situations. So when you're multiplying 50 by 60, you're not saying, okay, what's 50 60 times? Although you might, that's a different conversation. You'll say, well, I know that 5 times 6 is 30. Could that possibly help me figure out what 50 times 60 is? You know, so that's kind of what I'm getting at here. So yeah, you could make a truth table, but then at some point you start realizing, well, I'm making a truth table for the same problem over and over again. At some point, I probably want to see what the whole point of this thing is, right? And so in the previous example, let me just put this aside for a second. And I'm going to do the old classic teacher writing. We know. I always hated when teachers did that. It was like, do we know? I think you know, but I don't know. So do we know? But anyway, up here, they told us that P implies Q and not P or Q were logically equivalent. All right. So what we say now, and we proved it. We proved it with the truth table. Right? This is a proof. We did it by case, which is a brute force way of going about it, but we did it. We proved we did our very first proof. Well, first real proof. Right. So we now know this to be a fact. We can use the triple equal sign, that magical triple equal sign, because now it's a fact. Right. Now it's not as elegant as a squared plus b squared is equal to c squared, you know, the old Pythagorean theorem, but it's something. Right. So anything that has this same form is also going to be true. Right. So I look at the structure of what we have here, and it looks pretty similar. I mean, there's some knots where I wouldn't like them to be, but they're there. Yeah, you know, like we have the conditional, we have the or. You know, we're looking pretty good here. Right. So what I'm going to do is I'm going to create some let statements. Right. Everybody loves let statements from algebra. It's like, why do we have to write the let statements? Oh my Lord, they help so much. They don't always help with the algebra, because if you know, like, or write an equation, M represents the amount of money, P represents the amount of papayas. It's like, okay, well, we could have used X and Y. We could use, like, you know what I mean. But here, defining our variables means a lot. So what I'm going to do is I'm looking at something that's got the same structure. That P, I'm going to let that be F. So I'm going to let P be equal to F. And I'm going to let Q be equal to not S. All right. So this is a valid sentence. Right, because it's taken, the F is taking on the role of P, the not S is taking on the role of Q. Right, they're the understudies. So now what I want to do is see if this will be a true sentence based off of these substitutions. So what I'm going to do is I'm going to replace the P in here with an F. And I'm going to replace the Q, the wrong thing, the Q over here with a not S, because I'm saying that that's what they're equivalent to. Now, some people look at this and say, well, I'd rather make the truth table. I understand. But you'll see, the more you get the hang of this, the easier it gets. I guess that would be true for anything. So, not, if I'm making the substitution here for P, replacing that with an F, I would get a not F, because the not is still part of the expression. Right? The Q gets replaced with an entire not S. So if I made the substitution of F for P, not S for Q, into the rule I know to be true, what I get as a result is something that is the same as what they're telling me. Right? Now, like I said, disjunctions are commutative. So when I say not F or not S, that's the same as saying not S or not F. So they are equivalent to one another. Right? And so therefore, these two expressions are equivalent to one another. Right? So when they said determine if they're logically equivalent, we just did by substitution. Right? So if I eat the right foods, then I don't get sick. I don't get sick or I don't eat the right foods. You know, like looking at that just without really, I mean, it's kind of mind bending. That second sentence really kind of blows your mind. That's why the symbolic notation can be really helpful, because you look at it and say, well, I don't get sick or I don't eat the right foods. How on earth does that mean the same thing as if I eat the right foods, then I don't get sick? Because the first sentence makes perfect sense. The second sentence is like, what? Right. So now you think about, I mean, I know this is beyond what you would be expecting in a geometry class, but if you were writing a contract and you wanted to get away with something, you know, like slip in something in the terms of the contract that maybe the recipient of that contract wouldn't notice or wouldn't pick up on. The simple way of writing it would be, if I eat the right foods, then I don't get sick. If I come to work, then I don't get fired. If I don't get fired, or I didn't come to work. That, I mean, that's a really weird way of writing it, right? But it means the same thing. So you write it in that way, and you pull the rug out from under somebody, or the wool over somebody's eyes, or whatever term you like. Right? So the remaining problems here are more truth tables to prove things, but you see we're working towards the laws of logic. All right. So we're gonna take another 5-minute break, and I'm gonna, well, let me leave this up on the screen so you have it. But we'll take 5, and then I'll talk to you about the assignment. You'll have 2 weeks to complete, and then, you know, that'll be it for tonight. But the assignment takes a little while, so I want to do a demonstration. The second part, there's 2 parts to it. The second part's a little funkier, so I definitely want to take the time to walk you through that. But let me pause the recording.